So today we're going to cover random vibration, chapter 8. So I'll give a brief introduction, talk about a little bit about the statistics, okay? Talk about probability, mean and standard deviation, some characteristics, we'll do an example, and then I'll talk about Gaussian, which is a certain distribution or certain, certain process that occurs very frequently, normal distribution. And then we'll talk about random processes, talk about power spectral density, and this is where it sort of applies to what we're doing, response of a system, and then we'll do a couple of examples, and then lastly I'll just a brief mention of things called fractal plots and surfaces as well. So up to now, we've been dealing with what's known as deterministic systems. And deterministic means that essentially we know the values for x, which is displacement or velocity or acceleration, with some degree of accuracy and precisely. Okay, so we know those values. But in reality, often certain processes cannot be precisely predicted. Okay, we don't know, and this is called non-deterministic. The other word that we can use is random vibration. Okay. And with random vibration, details are often unknown, so we don't know the values for x dot or x double dot, displacement, velocity or acceleration, but we do know some characteristics of that system, and those are generally given by some sort of form of statistical information. Okay, so that can be obtained or is determined, okay, or is available, and so that's the difference. Okay, this time instead of dealing with specific values of displacement or velocity, we're going to be looking at the sort of statistical information about that thing. So an example of a random vibration would be something like a road surface, okay, or some manufacturing process that has some degree of variability in it. We don't know specifically, what is the displacement of the road surface as you go along, but we've got an idea of, what is the variation in the road surface as you go along, and that sort of stuff. So you've got some statistical information about how the random, vibration occurs. So if we look at probability, you've got a random variable x, so the x could be a length of a manufacturing process or something, and you take a bunch of, in the case of manufacturing, you've got n number of widgets that you're making that has this variability x. The probability that a chosen value of that dimension or whatever in the manufacturing process is smaller than a certain limit, I guess, which is given by x with that squiggly line underneath. The probability of that is you take the number of widgets or whatever that has this case, and you divide them by the total, and that gives you the probability. So say I'm making 10 widgets, okay, and there's a certain dimension that has a random component to it, and I'm looking for the dimension where that is less than, say, 5 millimeters or whatever. Then I look at all the parts that have that dimension of less than 5, and I divide them by the total number of parts. So my probability of getting, my widgets will be that number divided by the total number of widgets I've made. Okay, that makes sense. Yeah, if you're making 10 things and you're looking for the ones where the dimension is less than, say, 5 millimeters, and there are 5 of them, then obviously 5 over 10 gives you 1/2. So the probability of getting this being the case is 0.5. Okay, makes sense. Straightforward. P, which is known as the probability distribution function, it's the same thing, but as n approaches infinity. Okay, so you get the same sort of process. And like I said, as n approaches infinity, you're reaching this limit condition. And obviously, if big P is a half still, then obviously that's I know that half the time I'm going to get a part that meets that limit that I've set. Now, if we take the derivative of P, okay, with respect to x, this is known as the probability density function, the PDF. Okay, and you'll come across this time and time again as you do engineering. But yeah, PDF, probability density function, that's denoted by little p. Okay, and so obviously if little p is the derivative of p to the x, big P, okay, then you can take the integral of p and little p, and you'll get big P. Yeah, and the integral is important because that gives you the area underneath a curve. And we know that the integral of little p dx, this always equals 1. Okay, Because essentially what we've got with this function is you've got a curve that represents all the possibilities in terms of some random vibration, okay, underneath the curve, and the integral from minus infinity to positive will always be 1, okay. So if your curve looks, I don't know, like some sort of bell-shaped curve or whatever, then every value, every possible variation in that thing that you're looking at, the x, that dimension or that variation or whatever, will always occur within that, underneath that curve. And so here's a particular example. We have what's known as a normal distribution, but essentially what we've got is in this case we've got a number of samples, okay, and a number of occurrences. So specific values or whatever you take. You take this example. We know that this is going to be quite frequently. I'm going to have this this value of this sample. Okay, so this could be my x term or whatever. And so I've got 8,000 of them, whereas down here I've got very few of them, and I've got 256,000 samples in a sense. Okay, so this could be my so like I said, the manufacturing process. My nominal value, the thing I set my dimension to, was 130 millimeters or whatever. But because of the manufacturing process, there's going to be some variability in meeting that target, and the distribution I get looks like this. So for 256,000 points, I could draw a histogram. So I measure each one of those, and I get a distribution. Now the PDF of that obviously looks something like this, okay? And so that's my distribution. And so the area underneath this curve, okay, is equal to 1, because the chance of me having a part that's within this sample, within this distribution, is 100%. Anything that I make will be underneath that curve. Okay, so that equals 1. The area underneath that curve equals 1. Now, to find the mean, okay, you have your function, which is your distribution function, okay? Sorry, if f(x) denotes the function of the random variable, okay, then the expected value, or what's known as the mean, okay, so this is 3 ways of referring to the same thing. You've got mu, or expected value of the function, or the mean of the function there, is the integral of that function multiplied by p of x times d of x. And so, if my function is simply x, then equation 1, which is this one here, gives the expected value, also known as the mean value. Okay, so you take x px dx, and you integrate that between minus infinity and infinity, and you get your mean value. Okay, you were probably expecting, you add them all up and you divide them by the number of samples you've got. Well, that's the case when you've got discrete functions. Okay, here we're talking about a continuous function, and so you have to use integration instead of a sum. If f of x is x squared, then we get the mean value, the mean square value. Okay, so you essentially put x squared into that integral and integrate between minus infinity and infinity, and you get your mean square value. And RMS, root mean square, often crops up when dealing with random vibration, and that's simply the square root of your mean square. Okay, so you take the square root of this term, which is there, and you get your root mean square. Variance, okay, of x, denoted as sigma x squared, is defined as the mean square value of x about the mean. Okay, and so to get it, you go through, you take the value of your sample minus the mean, you square it. Okay, you integrate it with p of x. So going through this process, obviously what I've done here is I've expanded this out. So you get x squared minus 2 x bar x plus x bar squared. Okay, this is known as this is a constant. Okay, so this is very relatively straightforward. We don't have to worry too much about that. What I've done is I've basically separated the integral into 3 different integrations with each of these coefficients. Okay, like I said, this is a constant. Okay, so it's constant times by 1, because the integral of p of x is 1, so that's where this comes from. Okay, here I get 2x bar squared, and here I get x squared bar. Okay, and so the variance is known as the mean square, which is this one here, minus the mean squared. Okay. And if you take the square root of that, you get what's known as the standard deviation. Okay. And if both the mean and standard deviation are two important quantities when analysing random processes, and if the mean is 0, the standard deviation and the root mean squares, square values are the same. Okay, and that makes sense. If your mean is 0, then obviously the square root of this is the square root of this, and so you get the standard deviation is simply your RMS value. And perhaps it's easier if we look at an example. So, again, the manufacturing process, I'm making some rotors and they've got a certain eccentricity about them, okay, and they've got a following distribution. So I've got between 0 and 5 millimeters, I've got this function is my probability distribution function, okay. So it looks, I mean, if I was to draw it, it's kx squared, so it's obviously a parabola. Let's see whether this is working. So if this is x, this is my p of x, I'm looking at something that looks like that, okay? Between 0 and 5. So if that's 5 and that's 0, then this is my probability distribution function. And the limit of that, basically the integral of this between 0 and 5 is going to be 1. Okay, so the chance of me making a rotor with an eccentricity between 0 and 5 is 100%. Okay, there'll always be, and that could be due to the limit of the machine or something like that, that I can't make it more than 5 millimeters out of zinc. K is a constant that we'll determine. First off, we've got to find A, the mean. Oops. We have to find the mean, the standard deviation, and the mean square value of the eccentricity, and B, the probability of realizing that x is less than or equal to 2 millimeters. And so we can go through the process to find the mean. So first off, we need to find k, okay, because we need to work out these values. And so we know that p of x dx, the integral between minus infinity and infinity, is equal to 1, okay. Obviously, we don't need to go from minus infinity to infinity because we know that our limits of our integration are 0 and 5, so we can use them as our limits. We stick in our function p of x, kx squared, the x, obviously that we know must equal 1, and so if you multiply it out, if you take this integration, you get k times x cubed upon 3, which is here, between 0 and 5. Obviously 0 in here is 0, okay, so we've got k times by 5 cubed, okay, which is 125 divided by 3 equals 1. If you rearrange it solving for k, you get 3 divided by 125 is equal to k. So we've got a value for k. To find the mean, you stick in x into this integral, okay? So this is the mean value. You've got your x, px in here. So again, we stick in, we've got x times by k x squared, which is our px term. So obviously the k is a constant that can come outside. You've got x cubed in here. You integrate x cubed, you get x to the power of 4 divided by 4 between 0 and 5. And so you stick in, obviously 0 in here is 0. 5 to the power of 4 is 625. And you multiply that by k, you get 3.75 millimeters. Okay, so the mean value of that distribution that I drew, okay, is that parabola, okay, is going to be 3.75 millimeters. So my parts, yeah, if I, like I said, if I took a certain number of parts and I measured them and I added all those measurements divided by the number of samples, I'll get 3.75. Okay. But this is the way of doing it using integration. I didn't need to sit and measure it. I knew the distribution, and so I can integrate that and I get the result. That means to get the standard deviation, I need to follow this process. I know that we've got the standard deviation is the mean square, okay, minus the mean squared. Okay, so to get the mean square, I put x squared into this integral. Okay, again, k will come outside. Okay, and I end up with x squared times by x squared in here, which is x to the power of 4. Obviously, this becomes x to the power of 5 divided by 5, between 0 and 5. You go through and measure it. 5 cubed, so 5 to the power of 5 is 3,125. Multiply that by k, divide by 5 over here. And then obviously I minus my mean value squared, and I get 0.9375. And to get the standard deviation, we can see that you take the square root of that and you get 0.9682 millimeters. So my standard deviation is almost 1 millimeter. Okay. And obviously the mean square, I just use that process that I used here. So it's just this side, it's this process to get this term. So it's this bit, this bit, this bit, and this bit. Okay. And if I do that, I get 15 millimeters squared, and the RMS obviously would be the square root of 15. Now, to work out the probability that my eccentricity is going to be less than 2, okay, instead of integrating between 0 and 5, okay, we know that that equals, if I integrate this between 0 and 5, I get 1. Yeah? But obviously, if I'm looking for the probability that that eccentricity is less than 2, I integrate between 0 and 2. And so instead of having 0 and 5 here and 0 and 5 here, I've got 0 and 2. And so I integrate between 0 and 2. 2 cubed is 8. Okay, so I get 8 divided by 3, multiplied by 3 over 125. So that becomes 8 divided by 125, which is 6.4%. So the chance of me getting, so let's say that my variation gives me up to 5 millimeters of eccentricity, but what is acceptable in terms of a manufacturing process is 2 millimeters of eccentricity. Then I know that if I run my manufacturing process, I'm only going to get that part 6.4% of the time. So I need to do something about my manufacturing process, quite obviously. Okay. Now, a Gaussian process or a normal process is something that occurs very commonly in nature and in engineering. Okay, it's called a Gaussian or a normal process, and the process is given by, okay, this distribution. Okay, this looks quite complicated, but you probably much more, you'll recognise that distribution. That's the equation. Sorry, that's the plot of this equation. Okay, and it becomes a lot simpler if your mean is 1. If your mean is 0 and your standard deviation is 1, then obviously this becomes a lot simpler. This suddenly becomes x divided by 1. So this just becomes 1/2 x squared. And obviously down here, 2 pi times by 1 squared is obviously 1. So you just end up getting a much simpler equation. But that's accommodating all means and all standard deviations. And so like I said, you get a plot that looks like this. Then depending on your standard deviation, it either becomes wide and low or short and tall. Okay, because the area underneath this curve is 1. Okay, so all my, if my process has a normal distribution, then it's got this bell-shaped curve, which is the other term you may have seen, and every possibility, every possible value or variation will be under this curve somewhere. Okay. Like I said, this occurs in engineering, it occurs in nature. If I took a large enough number of people and I measured their heights, okay, the distribution of that would be a bell-shaped curve. Okay, if everybody of the same adult age and stuff, you get a bell-shaped distribution. Okay, so most people will be around the mean, but obviously as you get very, very tall people over this side and very, very short people over here, but you get this bell-shaped curve. And like I said, engineering processes will often have this shape as well. Okay, so it's worth bearing that in mind. In terms of the standard deviation, there's some interesting characteristics. Okay, the probability that my x value is going to be between, c will be a certain value, 1 standard deviation. Okay, so I could work out the probability with that distribution that my c is between minus 1 and 1. So between 1 standard deviation of the mean, I can take the integral of my p of x term. Okay, knowing standard deviation and my mean value. Oh, sorry, this is assuming mean is 0, so I don't need to worry about that. Okay, I can take the integral and I get certain values. Now, like I said, if I'm looking between 1 standard deviation and the other, I know that 68% of the time I'm going to be hitting that variation. If I up that to say I'm looking between 2 standard deviations, I know that 95% of the time I'm getting that. 3 standard deviations, we're getting close to 1, and 4 standard deviations, I've got almost every single sample in there. There's only really the extremes and the lower extremes.